Hello, today I wanted to work towards cubic splines by way of example. I wanted to start with a polynomial interpolation example. We have some book data in table 17.1 where we have some temperatures or some x values, and then we have some density or y values, and we're sort of focusing for a polynomial interpolation. We might be focusing, say, on temperature is 75 degrees, for example. We want to fit a cubic using 4 consecutive locations there. And so if it's an interpolation type of thing, you might kind of neglect the other points. We might have n is 11 points in our full example, but if we're focusing on maybe what's happening at the x equals 75 or the temperature 75, we may pick those 4 and try to fit a polynomial through those. So that is a polynomial interpolation type of thing, and I'll show you how that looks. So if I do that, I might plot all the data in blue. Those are going to be 11 data, so you'd have 10 line segments between them. And then if you focus in on just the points around the 75, you're going to end up with that cubic, and I can sort of zoom in and you can see the blue is the line segments between the data, and then the 4 data points that I'm creating this interpolating polynomial looks like that, and then the cubic does. And then when I zoom in more and more, I see, hey, the cubic interpolation is going to give me that 75 and 1.013 as opposed to maybe the coarser line segment there in blue. So that's polynomial interpolation, and it sort of kind of sets us up for what the spline might look like. So for cubic spline segments, we're actually going to use all of the data, all 11 points, and we're going to end up with 10 cubic spline segments situated between each of the points. And that might sound kind of crazy, but what you do is you actually use the extra flexibility there to make the data smooth at each node, making the data sort of match first derivative at each interior node and also second derivative. So there's 10 cubic spline segments in this example, and the first segment is going to be between -40 and 0, and the second segment between 0 and 20. So we'll kind of focus in on that node right there to see what the splines, how the transition of the splines look. And then there's going to be a spline between 50 and 100 at that 75 location that we're sort of interested in. So here's the resulting graph, and I kind of left the interpolation cubic segment. I went ahead and left that in there, and with the red dotted with those lines that I've shown you initially. And then the cubic spline is going to start for all points. It's going to be in dark green, and it's kind of hard to see it as you look at the full picture. But let's see if we can zoom in. At that zero temperature zero temperature location, and you can see that first spline segment very nicely fits up against the second spline segment in green. You won't even notice those are actually 2 different curves, but they match slope as well as second derivative. You can see how that's different than just the raw data where you have the faceted line segment. So that's at 0. And then if I zoom back out and then maybe zoom in on that area of interest, this temperature 75, x equals 75. So we're going to zoom in progressively more and more at 75. And the dark green would be your spline. And you can see there's going to be a difference between that and the interpolation result. So if we were going to report a spline result, we'd report that a little bit lower, than the polynomial interpolated value, and both of those being lower than maybe a first order linear interpolated value on blue. So anyway, so I think that is a really good example of cubic splines and kind of what the lay of the land looks like on that. Hope you enjoyed it.